Well, black screen. Good morning, everyone. It's not morning, it's afternoon. Good afternoon, everyone. I was so close. It's only 6 minutes from being a morning. Good afternoon, everyone. I hope you have all been well. Hope you all had an exciting evening yesterday. And I hope that people have started their assignment as well. And are doing their assignment. Lisa's asked, hey, just curious when our more recent lab and weekly code tests will be released. The most recent marked one I have is from week 4 for both. It has been set off, but because of those CSE server issues, it kept interrupting when we set off the marking. So that's why some of them haven't been released. So they are running, they are happening because we tend to run them overnight so they don't interrupt anyone using VLab or anyone using anything else whilst it is running. So it is coming, and I've put we're just also gathering all the stats on we're almost finished marking assignment 1, so hopefully we can get those marks to you this week sometime as well. I will keep you updated. So you will have, we're going to try and get as many marks as possible to you before the exam as well, so that you know where you stand. Okay, let's start. This is going to be the last lecture where we're going to do some new material. Next week is just going to be talking about the exam and also doing a lot of revision. I really hope to be able to squeeze in some revision questions and some questions that might be similar to the way exam questions are asked, so that you get a little bit of practice with everything. And to that end, I can see that only 33 people have voted on what they would like to do next week. So in the revision, so this is hang on. Yeah, you couldn't, I did a third one and it worked. Because apparently when you put it in announcements, the poll doesn't let you vote, which is terrible usability, and someone definitely did not test that properly, because if it's not going to work, then why on earth would you allow someone to insert it into a message? So anyway, it is working now, so if you can please follow the link. It is called Week 10 lecture revision. It's inside the lectures chat, so I've put it, I'll show you. People are voting now. I can see, there we go, on this screen. I'll just hide this way. Okay, so the new poll is located in here. Let me post it into the chat. And then you can please have a vote. You can see, there we go, that's the one. And you can please, oh, there we go. Excellent, people are voting. I like to see that, because I want to be able to do stuff that you will actually find useful next week as well. That will help you out, hopefully, for the coming exam. I can see lots of people want to do linked lists. This is great. We can do a lot of linked lists, so I will hope to do that on Wednesday. And then pointers, strings and chars, fantastic. Yep, all of those, good. Maybe strings and chars on Tuesday. And then pointers, maybe we'll start, and then pointers and linked lists on Wednesday, and we can do quite a bit with that as well. And recursion is accessible, right? Okay, so I really want you to enjoy this recursion lecture and to just really have some fun with it. So it is accessible in that it's going to be probably in the short answer questions. You're not going to be expected to write the practical coding questions with recursion, but you can if you want to. Okay, so yeah, so there we go. Jess, I was cruising along and then linked list hit, and now I'm suddenly the Titanic. No, not the Titanic. Absolutely not. No, we will recover you. We will lift you up. There is no, we will lift you up. Don't worry. Linked lists, I think, such an abstract concept. Like, why do you have this weird data structure? And how do you use it? Where does everything link? It is one of the best data structures where binary trees also, you want to draw that up. But linked lists, you want to draw it. You really want to draw up the diagram, because it becomes a lot more obvious what's going on. What was the average final mark for the exam for T2? Oh gosh, I don't know. I would have to look that up. But to make you feel better, think it wasn't. No, I can't say because I don't know. I can't say. But you know, people did pretty well. Like if you have been doing well in your labs and in your, you know, assignment stuff, if you've been able to do stages 1, stages 2, attempt stage 3 or whatever in your assignments, it's a good indication that you'll be able to do you know, question 1, question 2, probably question 3, question 4 in the exam as well. And we'll talk more about that next week. The exam questions are also ranked, and I'll give you some tips how I think you should approach the exam. But obviously those are my tips. That's how I would approach the exam if I were a student. And you would also, you know, some of you would work differently as well. For example, I'm the person that goes from the beginning to the end and has to be consecutive. I know other people can jump around a bit more and feel more comfortable with that. So, you know, use your own strategies as well. Use what works for you and how you see things, you know, coming together as well. But we will talk more about the exam next week. Is there theory in the exam? Not like, I think you're asking it in the sense of, is the exam going to have a question like, what is an abstract data type? And you have to write 2 sentences. Is that what you mean, Sienna? Because in that sense, no, there's no theory like that. It's more, do you understand the theory to apply it almost? You might be asked, you know, what does this look like or what does that look like? So you don't have to have definitions there, but you have to be able to answer questions. There is a fly on my screen and it's just crawling about and it's very distracting. Yeah, so let me know if you have any questions. Obviously, just pop them in the chat. And Tom Killingback is in the chat once again, answering your questions. So there's, you know, hopefully we can get to everyone's questions. Is the exam like a longer version of the weekly tests? It is indeed. It is like a longer version of the lab, almost. So it's like the questions are of different difficulty, just like in the lab you have different difficulty as well. No pseudocode questions. I can't think of what's... no, but there, if we give you a snippet of code, you might be asked to understand what that snippet of code is doing. Is the exam 6 questions of all equal marks? No, the exam is going to be 20 short answer questions, which is 1 mark each, so 20 marks, and 8 10-mark questions, which is 80 marks, so together 100. Does anyone get 100% in the final? I have never seen that happen. There have been a few people that have gotten close to that, and I'm not really sure, like, that's, yeah. That's completely, yeah, it's an anomaly to get 100%. I've not really seen it. No, assignment 1 marks are not out. We're just finalizing everything and making sure that the marking was done consistently across all the different tutorials. So we should hopefully have them by the end of this week, at the latest very early next week, and I will update you in the announcements. Did I say recursion is in the final? It is in the final in the sense that you might have a few short answer questions about it. You will not be expected to use it to write any of the practical coding questions, but you can if you want to. And what is the correlation of lab and assignment marks to exam marks? It is pretty high correlation. Basically, if you have done well in the labs, if you've done well in the assignments, you will do well in the exam as well. So we are not trying to trick you. I really want to test you on what we have taught you. Similar style questions to the questions that you've had in your labs and in your weekly tests. We really want you to walk away from here actually having learned something. And so we are really testing what we have taught and the kinds of questions that you have done before so that you're used to seeing those types of questions. There will be a sample, there will be like a sample exam environment next week. So you'll log into it and you'll make sure everything is working, and it will have a few questions in there that are very much worded like the exam as well to give you a feel for what the exam looks like. There will also be a few multiple choice questions in there. Sorry, the short answer questions to give you a feel of that as well. And there is going to be an example of the hardest question on the final. So yeah, it's hard. Okay, so there's not going to be a past paper per se, but what we will have is revision questions for you that will have similar style to that sort of exam. Now, that exam that you're going to be sitting, it used to be a 3-hour invigilated exam, and we give 6 hours for it to give you time, in that online environment, to give you time to take a few breaks, and also to just, be able to have a snack, whatever else, if there's technical issues. So, it's designed to have 3 hours of consistent working time. You might not be able to finish it all, and that's okay. You get to a point where the marks are just not worth the extra time you're putting in. We will talk more about it next week. But yeah, there will be samples, and we will have the example environment for you as well, so that everyone knows what they're doing when it gets to the actual exam. And we will be online with you during the exam, so if there's any issues, we will always be contactable as well. Okay, that was a long spiel. I'm going to go back to the exam next week, so don't worry. We're going to talk about the exam in great length because I really do want everyone to go in there feeling confident and being able to answer the first. I would love it if people could attempt and answer the first 4 questions in the coding section. That is a great question. Is the difficulty going to be greater due to the added time? The only difficulty that is greater is in questions 7 and 8. And if you are aiming for a HD, then you would be attempting questions 7 and 8. Okay, let's go back to today. Recursion. Has anyone ever heard of recursion? Has anyone ever seen recursion? I have to say the first language that I learned when I first started computing was a recursion. It was a language that centers in recursion, and it left a pretty sour taste in my mouth to start with. And it took sort of a bit of time for recursion to really make sense. And there's a reason we don't teach recursion now as the first language that you do. I think you need to have some sort of understanding of computing and languages before you start looking at recursion. And then, in fact, recursion becomes quite neat and quite a nice way to do, to solve problems. And certainly some problems lend themselves really, really well to using a bit of recursion in there to have a really nice way to do it. And then some problems, well, maybe I'll hang the computer for you today so you can see it all crash and burn when recursion goes wrong. There's a few more questions about the exam. Is there any? I'm just going to quickly then go on a tangent and answer those questions because I think people are a little bit stressed. Is there any hurdles? There are 2 hurdles in the exam. One of them is that you must be able to answer an array question, and one of them is you must be able to answer linked list question. And that's either question 1 and 3 is the array questions, and question 2 and 4, one of those is a linked list question. We'll talk more about them next week. Which of the questions are the ones required to do to pass the... Oh, okay, so there you go. Those were the questions that you need to do, the hurdles. I would recommend just doing question 1 and 2. They're both 1 dot difficulty. So if you've been able to do 1 dot difficulty in the lab, you should be able to do them in the exam. Theo, if I do the first 4, I'm going to get myself a Happy Meal. That is a great idea. You're going to get yourself... That is a great idea. Just celebrate. Exactly. Do we have auto tests in the final exam? You do indeed have auto test. So there's going to be, but the auto tests, again, as the questions get more difficult, the auto tests, we don't give you auto tests for every single case. You need to do your own testing as well if you want to make sure that everything is working. For the first few questions, the auto tests are a lot more comprehensive, but then it does go down. Okay, yeah, definitely. If you use a pointer in there, that could get very, very loose. I think it's only in discrete maths in high school you would have done recursion, and yeah, yeah, you're going to get a serious overflow if you recurse till the cows come home. And yes, also style tested for the questions. No, it's not. You'll be happy to know style is not tested, but we do manually mark your questions, especially the hurdle ones, because we want to give you the best chance possible of passing everything. So please indent your code, make it easy to understand so that we can mark it easily as well. Yeah, auto test is going to work. Yeah, auto test will work for you. Yes, for the revision, absolutely. And will you have access to 1511 style? I think so. From memory, you do have access to 1511 style, but you don't. We don't mark you on style in the exam. Okay, back to recursion. Here we go. That was our vote. I'm pleased people are voting. It's still looking very similar. So linked lists is winning the fight. So I think I'll do a whole day. Okay. Now, when I found this image, it made me so sick. I can't stop looking at it, but this is like recursion to the max. Okay. Just, giving you the vibe of what recursion is. Think of a function calling itself and then calling itself again and again. I think I'm making myself feel sick again with this picture. Again and again, again and again and again and again, and you keep calling it and keep calling it and keep calling it, and you recurse and recurse and recurse until some sort of stopping condition has been met and you need to stop. Okay, I need to change this screen. I didn't realize this picture really does make me feel a bit ill. Hope no one else felt like that. A bit green. So kind of, it's like a while loop that, yeah, it is kind of like a while loop, but instead of just doing it with a variable, you have a stopping condition for, when are you going to stop recursing? When are you going to stop calling a function? So what you're doing is you're calling a function over and over and over and over again. So recursion is really used all around us, and it's a different way of thinking. It's a different way of solving problems. So in computing, it's like you have to go backwards to go forwards. And if you're a bit confused, welcome to recursion, but it does get better. Once you run a few questions, once we do a few questions today, it will make a lot more sense how it works. And again, I strongly recommend drawing a diagram because that really, really helps. Yeah. Oh, like when you have that Zoom call, and then it like lines up all the screens in, that makes me feel sick as well. Okay, so I just thought these are cool. These were old like ads, I suppose. One is for butter, one is for chocolate, hot chocolate, and they kind of use recursion because here the person is holding the thing, and then there it is again, and here the person is holding the actual cocoa tin, and there it is again, and so it's like the function inside the function inside the function inside the function. So that's basically recursion. You just keep calling things back and again and again and again and again and again. So what we'll do, I think, is we'll write an iterative function. So it's usually called an iterative if we do it the same way that we normally do, which is just like solving it step by step kind of thing. And then we will convert it to a recursive function, and we'll draw it out so that you can see where it's all coming together or falling apart. I mean, you can see where it all comes together. Okay, so the first one we'll do, let's say we've got a linked list, okay? And I thought, here we go, let's do a linked list problem in here as well, so we get a little bit more practice with linked lists as well. So I think the problem that I want to do is sum up all the nodes of the linked list. I have to say, I'm still feeling sick from that picture. I don't know why I showed you. I knew that it made me sick, and now I feel very green. Okay, here we go. So let's say we want to sum up all the nodes of the linked list. So I want to do 1 plus 2 plus 3 plus 4 of the linked list. And then I want to output the sum of what on earth is going on. So in this case, what will be the output? 7, 10. Well, that was nice. I'll come backwards. Okay, so let's go to our code and let's write this function. I won't show you the code so that you can get some practice doing it. It is, yeah, I very deeply affected by that T. Okay, where are my lecture slides? Off, V lab on. Okay, so I'm in the week 9 directory for the live code. And what I've done is I'll just show you what I've quickly done. So inside the week 9, I created a directory called list. And inside that list, I have placed 3 files. These 3 files are from our week 7 and week 8, what we were doing with linked list. But to make it all easier and all in one place, I've placed them into week 9 as well. And so what I did is I've opened up those files so that we can keep working in them. So then it's easier because then we already have our print function as well. So we don't need to worry about all of that. And a way to create the linked list. Wouldn't it be funny if I vomited on camera live on YouTube? Okay, here we go. We're going to sum things up. Let's do it. Okay, all right. So let's say we have our linked list. Let's draw it out so that we know what we're doing, and then we're going to do the code, just our normal code for it. Okay. So our linked list currently has 4 nodes, I believe. I'm specifically not going to make them look pretty and line up, so that just to underline that point that when you have a linked list, things are spread out everywhere in memory. It's not necessarily in a perfect, straight line sort of format. So what happens? Okay, let's see which numbers we're putting in. Let's go to our main. So we're putting in 4, 2, and 1. Oh, there's 3 things. Okay, well, I'll just delete one. Okay, so in that case, I have, so at the head is the 1, and then I've got my 2, and then I'm going to my 4. And 4 is the last thing, so it's going to go to null. And in here, this is going to be my head pointer. Okay, great. Okay. Now, I want to go through that list and sum it up. What will be the return of this function? What will we return if we have a function? You can't access the live code. Let's have a look. Okay, hopefully you can access it now. Okay, yeah, okay, so we're going to return an int because it's going to be a sum. I'm going to be awesomely clever and call it sum because I think that's a good variable name. And now what are we going to give it to sum up? Okay, excellent, good. And what are we going to give it to sum up? What should we give to sum up a linked list? Yeah, well done, well done. I'm going to give it the head. So I'm going to give it the list that I want to sum up. Fantastic, well done. So I'm going to give it a struct node head of the list, because if I give it the head, that means that we will be able to go through everything there as well. Okay, fantastic, great. Okay, now, okay, so you already told me that I'm going to return the sum. So I'm just going to write here return sum. And that must mean that I need to have some sort of sum. So I'm going to have an int sum and I'm going to initialize it to 0. I might call this sum list. Okay. All right, excellent. So now I want to go through this list and I want to add up each node. So add up each of the data sections of each node. Okay, so what is the first thing that I do? I want to have a way that allows me to keep track of where I am in this list. So I will create a pointer, a current pointer. You've seen me do this, I think. Maybe it's giving you nightmares now. So I'm going to create a current pointer and point it to the head of the list, which means I've got this pointer current. That's the pointer that I'm going to use to traverse through this list. And I'm going to point it to this head that is given. Excellent. So now what that means is I have current is set over here. So it's pointing to the head. Okay, so current is sitting over here. Now, how do I move on to the next thing? Okay, so we've got whilst head next. So let's use the current to move through it. Let's not modify where the head is pointing so that we kind of always have access to where the head of this list is at. So if we have, although in this case it doesn't matter because we're returning sum and we have head elsewhere, but good practice to just use something else. So we're saying whilst current next is not equal to null. Okay, what that means is whilst current next, if current is over here, then I'm going to stop. So I'm going to stop as the, no, that's not, yep. And then current next is equal to null in this case. So over here is where current next is equal to null. So if we do it this way, let's have a look. And then we're going to increment as well. I saw someone write current is equal to current next. Okay. And how do we add it up? How do we add up the sum? Who's got ideas how we can add up the sum? Yep, sum is equal to sum plus current data. Well done. Yeah, and someone is saying it's not current next is equal to null. Okay, good. Okay, we're going to see what's going on. Okay, so let's have a look. So we've got whilst, that means sum is equal to sum plus current data, which means, oh, not next, current data, which means what it will do is it will take the sum and it will add the data point of what's going on inside the node. And then all I have to do is I have to return the sum of my, yes, Lisa, that's it. Yes, a few people have seen that we might miss the last one if we go until current next is equal to null. Well done. I was going to run it first to show when this happens. So that's very good. Well done. Good pickup. So if we stop here, whilst current next is not equal to null, what will happen is we're going to stop on this node. So when we exit this while loop, that means the condition will be that current next is equal to null, which means you're going to miss the last node. Okay. In this case, you need to go all the way to the end of our list. You need to go all the way to the end to the null point. So in fact here you have to go until current is not equal to null, because you need to go all the way through the list to add up every single node. Someone's saying they've got PTSD from their assignment. Yeah, I warned you, you're going to get some nightmares from the current pointers. Okay, so we now really have a nice little function that sums up the list for us. Let's have a look. Let's see it running. So first of all, I'll just place it inside my .h file so that so we've got here, I've got print list. Okay, and what I'll do is in the main, I'll also call it as well. So I'm printing the list, and then I'll do a printf by using that function sum. So printf, the sum of the nodes is %d, And at this point, I'm going to call the function SumList. And I'm going to give it the head. Okay, save, save, save. Let's run. And then we're going to convert it. Let's do DCC. Okay, great, it compiles. So if we run it now, we've got the linked list is 1, 2, 4, and the sum of the nodes is 7, which is correct. So that's pretty exciting. So we've got a sum working as well, and we've been able to see how that works. Okay, so now what if we try and rewrite this function in a recursive fashion? Okay, so let's try and do it as a recursive function. So I'm going to call it SumList recursive. Okay, I'm still going to have the same output and input, so I still have to give it the head so that it knows what list I'm summing up, and I'm still going to output the sum, so that doesn't change. But what changes is how we're going to actually do our recursion. So when you do recursion, yeah, well done. Okay, well done. Someone is thinking through with it. There's two things in recursion when you write your functions using recursion. The first thing is you need to think about what is my stopping case, and the second thing is what is my recursive case. Okay, sometimes it is easier to think of the stopping case when you've already thought of the recursive case, sometimes not so much. I would like to say again that it is a very different way of thinking. So the first few times we do it, it might make very little sense to you, and that's okay as well, okay? So in the case of a linked list, that's probably the easiest way to see when you would need to stop, okay? Because if I sum up all my different nodes, there's only one time I will stop, and that time happens when my head is equal to null. So if I've gotten down to this whole null section, that means I've finished doing all my nodes. So if I'm over here, now my pen's not working. If I'm over here at null, it means that I need to stop. I can't go on. So my stopping case is very highly likely to be when head is equal to null. But what would be my recursive case? So the recursive case is how will you keep going, okay? And in my case, what I'm doing is I'm adding up my node to the following node. So I'm adding up my current node to the one that comes after it. And then this one becomes the current, and I'm adding this one to the one that comes after it. So the recursive case is that I'm adding my current data. So let's say whatever is sitting inside the head, and I'm adding it to the next one. So whatever's sitting inside next in the data section. Ooh. Okay, so what this means is I'm taking what's sitting in the head and I'm adding the next one to it. Okay, and then I can keep recursing through it like that. But how? I haven't actually recursed here. All I've done is I've added two things together. And Tim's asked when head is equal to null or when current is equal to null. Okay, that is a great question, a really great question. And in this particular case, when we do recursion, we are going to not use the current, and I'll show you why in a second. Okay, so if my recursive case, it's when I keep calling the same function over and over again. So if my recursive case is going to be, I'm going to save it in sum as well, but if I do head data, and then I'm going to call my function again, okay? So I'm going to call this function again, but I'm going to give it the next thing. So right now, my head data is this one over here. So this is the head data right now. And when I call my function, I'm going to call it again, but I need to give it the next thing, okay? So I'm going to call this function, and the function is called with the head of the list, but I'm going to give it the next node as the head. So I'm telling it, actually, I want you to now go with the next one as the one that's going to happen. Okay, because what that will do is it will look something like this. Okay, and I'm going to draw it out for you. So on the first call of my function, when I first start out, I've got sum is equal to head data plus, then I'm calling my function again, and I'm calling it with head next. So what I've done, what that equals to is, I've got sum here. Yep, this is good. My head data is equal to 1. And then I'm calling this function again. And it's being called with head next. So it's being called with this node over here. So this node is the one that's going to be the head now. And I'm going to label it just so that you can see where I'm at. So this is going to be what's inside there. Okay, so I'm calling it now with this one. Okay, all right. Great. Now, I don't know. I'm going to answer this call now, okay, and run the function again for some list starting with this head, okay. So that means if I run it again, my sum is going to be the head data plus I'm going to call it again with the next one. So my head next. Okay, so that means that what have we got? Okay, if I've sended this as the head of the list, that means that this head data here is equal to 2 plus, I'm calling sum list again, and I'm calling it with the next one in the list. Yes, yeah, no, that's right. So I continually change the head so it keeps calling itself with the next node. Okay. So now I'm sitting over here. So let's call this one over here 0xbcc. Okay, so now I'm calling it with 0xbcc. Okay, great. So now I'm going to use this call now. Let me move this one up so you can see what I'm doing. And now this call is going to be again. So I've got sum is equal to head data plus sum list and the next, but in this case my next is going to be null, isn't it? So it's going to stop there. Okay, and that means my sum here is equal to the 4 plus, when I call this, this is going to be my stopping case. So in recursion, we keep calling, and it keeps calling itself until it gets to the stopping case. And then what it does then is it rebuilds itself back up. Okay, so now I know that the sum down here is 4, which means that I know that this is equal to 4. Okay, that means that the sum in this case is equal to 4 plus 2, which is equal to 6. Okay, and what that means is I'm now ready to go over here. So I've got the 1 over here, and I know that this is equal to 6 from the last one. And that means the 1 plus 6 is equal to 7. And that's what I will return back, and then I'll return back. So what happens is you keep calling the function until the stopping case is met. And once you meet the stopping case, you rebuild it back up with the results that you got from that function until you get back to your first call of that function. Okay, so let's try and build up what it looks like in code. Okay. So first of all, you always need to have, okay, Mary Claire, just wondering how we know that the head is being moved to the next node if we're not writing head. That's a great question, okay? So when I call my function, okay, so when I call my function again over here, actually I don't need to write it again, I'm giving it head next, okay? My function takes in a pointer to the head. So when I'm giving it the head next, I'm actually giving it a pointer to the head. So what I'm doing is I'm saying this is where the head is. And now run this function with the head being at this pointer. So what I'm doing is I'm shifting it up and running the function each time one node less, the next node, and then the next node being the head. So I'm reducing it down until it gets down to null, until it gets to its stopping case. So my stopping case then is if head is equal to the null, then I'm going to return 0, because if I add 0, it's not going to change anything. So that's going to be my last return over here. When sum list null, that's going to give me a 0. And that means that 4 plus 0 will give me the 4. So it's going to give me that first movement, and then I rebuild back up. So return 0. Otherwise, I'm going to have my recursive case in this case. And my recursive case is going to be that I'm going to keep calling this function, and I'm going to keep going until it just finishes recursion. So I've got if head is equal to null, this is called a stopping case. This is how I know when I stop. Otherwise, your recursion is going to be infinite and it's never going to end. And the issues that you're going to have with infinite recursion are worse than what you have with an infinite while loop, because you're calling a function each time. So you're going to overflow much faster. And this is called a recursive case. So this is what I do when I'm solving it with recursive. Now, when you are solving your practical questions in the exam, I really want you to use whichever one makes more sense to you. So if the iterative method makes more sense, use that. But this definitely makes sense in some questions. And as you use recursion more, it makes more and more sense as well, much like everything else. So I'm never changing the head pointer. What I'm doing is I'm sending it a different pointer to the head each time. So I'm moving it along by giving it a different head each time. Okay, so let's see it run. How about that? Let me copy this into my .h file. So into the .h file, and I will also call it from here. Okay, so let's do, I'm going to do this recursive. Okay, so now I've called the recursive function instead. Okay, let's see if it works. Oh. Compile. Fun. What have I done? Oh, okay, yeah, okay. I've created this inside these curly brackets. And remember that it only lives inside these curly brackets, okay? So this is not really, it's going to die, and then I'm going to have nothing to return. So really, I want to return it here straight up. So I'll just cut this out and return in here. Save it again. Let's run it again. Yep, good. Okay. And now I'll run the program. And fantastic, it seems to work okay as well. Now with recursion also, what you'll notice, if it's making a lot and a lot and a lot and a lot of calls, which we'll do with another like example with numbers, what we'll see is I'm going to overflow a little bit to show you when recursion can get a bit nasty really, because what will happen is it keeps making calls out to its function. Maybe I can even show you what happens when I never end recursion as well. Could do that. Yeah, I could break things a little bit. Okay, well, maybe after the break we'll do that. Okay, so that's using recursion in that sum list recursive sort of way. What about if we tried to convert the print list function now to a recursive case as well? Because I think this one is quite an easy conversion, because it's really very similar to what you do iteratively as well. So let's try to convert the print list function to a recursive way as well. So I might call it print list and recursive. Okay. Great. Okay. So if we're doing it recursively, again, we're going to want a stopping case. Ooh, stopping vars. I don't know what that is. And we're going to want a recursive case. Okay, fantastic. What do you think will be the stopping case in the case of the print list? And it's going to be pretty similar because when you deal with lists, you usually stop when you get to the null, when head is at null, because that really, you can't really do much past that. Richard, if both are options and you feel equally comfortably with both, is recursion preferred? So recursion is preferred in some cases when you're just out, in industry or even just coding for yourself, because recursion, something that you can do in 20 or 30 lines, sometimes you can do with 2 lines in recursion. But sometimes what you can do in 10 lines in a normal function, you can also do in 10 lines in recursion, and then, what's the point in particular there? So Lisa, if head is equal to null, yeah, I think that's a great stopping case, because that means that we've reached the end of the line and we don't really want to do anything else. Now, when I reach the end of the line in my iterative function, what I do is I just print an X to finish up my, my final hurrah. I'm showing that that's kind of like the null bit. So that's what I'll do here as well. So when I've reached the null bit, I'm going to print out an X to show that I'm finished. So X and a new line. And then I'm going to have my recursive case. Okay, so this is where the magic happens. Okay, so yes, Theo, well done. Recursion is calling a function within the same function, and you keep calling that same function within the function and calling the function within the function until you reach a certain stopping case. So in here, what I'm going to do is at some point, I'm going to call a different function. So I'm going to print out my data because there's no really any way around it. So if I print out, nope. Okay, so first off, I'm going to print out what's happening, and then I'm going to call this function again, okay? So I'm going to call my print list recursive function again to print the next thing. What will I give it to call it again? What do you reckon I will give it to call it again? What will I call it with? And here, sorry, I don't have a current, so I'll actually... What do we reckon we'll call it again with? So do you reckon you'll call it again with the head? So if you're going to call it again with the head, you're going to keep giving it the same node, okay? Now I can see a few people are saying head next. If you call it with head next, that means you've just passed the baton to the next node. So if my head's over here, I've printed out the 1, and I'm going to say now my head is over here. So now I'm going to print out the 2. And now I'm going to call it again, and I'm going to say the head's over here, so I'm going to print out the 4, okay? So I'm moving it along by moving the head along each time. So that's right. So it's head next. Okay. So let's see it in action. That was pretty good. Well done. Let's see it happening in action. I need to actually, let me copy it into my .h. And I'll also call it in here. So instead of using my print list, I'll use the recursive function instead with the head. Okay, fantastic. Let's run it and let's see what it does. Okay, so let's run it. I forgot some semicolons. There we go. Let's fix that. Let's run it again. Excellent. We have compiled, and let's run it. And fantastic. It's printing out my list using the recursive function now as well. All right. Now I'm just considering, should I give you infinite recursion now before the break so you can see what it does, so that if my computer crashes, I can restart it during the break? No, my computer's not going to crash, but my VLab might crash. Because why would I crash my computer? I'm going to crash CSE's computer. No, not quite, but you know. Okay, who wants to see what happens if you don't have a stopping case? Who wants to see the magic of not having a stopping case? No one wants to see a breakdown. Yeah, all right, let's do it. Let's do it. Oh, Tom wants to see. Okay, well, I'm just going to break things out for you. All right, I'm going to do, you know what? I'm not going to kill the list. So what I'll do is I'll go out and I'm going to do a, okay, spelling, infinite recurse.c. Okay. Should I give you, I'll give you access to it as well. Okay, God, the spelling. Oh, because I haven't saved it yet. Okay, I'll do that in a second. Okay, so let's do a quick infinite recursion just so that you can see what it does. Okay, so I'll include my lovely stdio.h. Super exciting. And let's have, what should I do? Yes, I know what I'm going to do. I'm going to, oh. Okay, I'll have a main. And what I'll do is inside my main, I'm going to call a function message. Okay, and then I'm going to have a function message and it's going to be a void message. And what will I do? Let's printf a statement. Okay, can you see how I'm not going to finish this at all? It's just going to keep going. All right, are we ready for this? Okay, here we go. I really wish I didn't use the word infinite. Recurse. Okay, it's telling me it's not going to be good, and I'm going to ignore it. And I'm going to run it. Okay, and what you can see happening is it's just, I'm gonna keep it going, but you can see how much this is growing. It's still growing, 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 it's still growing. Oh, someone wants to call main recursively. Someone does want to have nightmares. Okay, we're still growing. I haven't crashed it yet. It's still going, still going. Maybe it'll crash after the break, but it will reach a status where it's going to say, I think I've had enough. I think I've had enough and it's all done. It's all over. I'm going to come out of it. It doesn't look like it's moving because, but you see how when I try to lift up the arrow, it's not letting me because it's still going. So yeah, it's just, there we go. And there we go. It's reached the end. And this is what you'll get when you kind of, let it go on and on and on. You get something that is called a segmentation fault. And you would have seen a segmentation fault when you have tried to dereference a null pointer as well and went a few other things. So it's this, and if you can see, I'm scrolling up right now. I'm scrolling up again. I'm scrolling up, and I mean, I can't even scroll up higher how many times it's given me a let's crash. And can I do it again? Can I do it again, but with a counter next to it so we can see how fast it's growing? I could, I guess. Why not? We could do that. Okay, so if we do a counter, let's do... Okay, let's have a counter. You know what? Let's actually, you know what? Let's take a break and then I'll set it off. I'll set it off afterwards. Let's take a little break because it's 1 o'clock. I'm going to leave you on a cliffhanger so you can see what happens. But then we're going to do more of these and I'm going to do a few more infinites. Why not? Just for fun. We might as well just crash things. And have a bit of fun with it. So let's take a 5-minute break. And then when we come back, I'm going to set it off with a counter so that you can see what it's doing exactly. And then after that, we're going to do a few more examples of using recursive functions because they're kind of fun. So let's take a 5-minute break now. All right, we're back. Let's crash some things. Crash and burn. Yeah, so this puzzle actually, it's the first taste of a concurrency, and it's used to demonstrate how deadlock happens between different processes and stuff in the computer. And there are a few different methods to solve it, but this is how you demonstrate what the issue is. Obviously, you can't just be like, well, I've always been like, just eat with your hands. What's the problem? You don't need a fork. But there we go. If you are interested, this is a pretty famous, the dining problem with the philosophers. It's a pretty famous problem. You can look up the solution. And if you are interested in how concurrency is treated in computing, this solution will give you an idea of what happens in deadlock. All right. I think it's time to crash some stuff. A few people, 130,832. Put your numbers down. What you reckon we're going to get to? What do you reckon we'll get to before we crash and segmentation fault ourselves? Okay, here we go. So what I've done is I'm calling the message now with an int num, because I can't make I equal to 0 inside my message function, because otherwise it'll keep knocking back to 0. I've said let's crash, and then I'm giving a number, and then I'm increasing the I, and I'm calling it with it. Okay, we ready? Oh, someone's saying 42. Maybe the number, maybe the meaning of life, huh? Okay, let's do it. Let's set it off. Compile. What have I done? Of course, I called it a num here, called it something else elsewhere. There we go, let's try this. Okay, here we go, it's given me a warning, but I'm a rebel without a cause. I do not care for these warnings. I'm gonna set it off anyway. Here we go, we ready? 42, it's gonna go way above that. Here we go. Here we go, gaining momentum in the 20s, in the 30s. When will it crash? I actually made Tom Killingback do it during the break to make sure that we wouldn't crash everything under the sun. Here we go, we're in the 80,000s now. It's still going. I feel like I'm a sports commentator. Hundreds, thousands, and still going. What will it get to? What exciting number? Oh, 170,000, and it's going pretty fast too. So we've surpassed, Tim, we've surpassed 130,000. I think we're getting close to the crash. Feels close. I don't know why, maybe, and we've crashed. So we managed to get 253,647 messages before we crashed and burned with a segmentation fault. So that was a bit unfortunate. So that's what happens when we have this case of infinite recursion. What you could do in something like this is you could have a stopping case of how many times you want to actually do this message. So you can send it with a number of times you want it to do this message, and that's your stopping case. When it reaches that number, when it reaches that particular number, then you stop. So, yeah. Okay, let's try to do a few simple functions now as well. Okay, let's try and do a few. No, it's not always the case. It's not always the case because different computers, if you remember, so I've used an int, yeah, in my function. I've used an int. So an int has also particular values that it can take, and I'm going to overflow an int for you in a second. So you can see what happens, and different computers also have different values, signed or unsigned. It depends what's going on, if you're signed int or you're unsigned int, and so on and so forth. So it depends on a whole bunch of things. Ray, what if you set it to 253,000% plus 1? It is hard to predict. It is very hard to predict because it depends like which computer I'm on and what I'm doing. Hey, Tom Killingback, what number did you get to? Can you type in the chat? What number did it get to on your machine? Okay. Whilst we wait for Tom to respond, where his computer crashed, I'm going to open a few more files. Okay, so you see Tom got to 256,180. Which one should we do? Let's do Factorial first. Ooh, Factorial. No, that's not what I mean. Factorial. Okay, so we're going to try writing a recursive function to calculate factorials. Okay, who remembers what factorials are from their high school maths? Maybe high school maths? Did we do it in high school? I'm too old. I don't know. But we did do it at uni, I'm sure. And for anyone that did 3-unit maths, I'm sure it brings back horrible memories of permutations and combinations, which they would have done. Oh, hated permutations and combinations. It still gives me nightmares. Yeah. Excellent. Everyone remembers it is the exclamation mark that gives us the factorial. So super exciting. Yeah. So if you have 1 factorial, it's just 1. If you have 2 factorial, it means 2 times 1. If you have 3 factorial, it means 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. Yeah, so you times them all out, starting from the number that you want the factorial of, and then you get the, the final answer. And so you can see how this would be, this is just prime stuff for recursion, because you're really doing exactly the same thing each time. So what happens in this case? What would be my stopping case, and what would be my recursive case now? Tim, you can't really know what it would crash on. It depends on a few things. You can't. It's very difficult to predict the exact crash number. And why does it crash? It is going to run out of memory. That is correct. Because I keep calling the same function, and if you remember yesterday, we talked about a function stack. So every time I call the function, it goes on the stack. So I've overflowed completely and utterly. Okay, so Lisa thinks our stopping case will be int is equal to 1. I like that. Yeah, so stopping case is really anything that is less than or equal to 1, isn't it? So my stopping case is if my number is less than or equal to 1, which you have said exactly. So stopping case is 0 or 1. In this case, I will stop and I will return something else. And then what would be my recursive case? What do we think would be the recursive case? If we're doing it with number, so if I'm using this int number, what would be the recursive case? So my factorial would be number times, yes, not plus, oh my goodness, times, and then you call the function again. Well done, number minus 1. Yes, you got it. Well done. Excellent. Fantastic. So my recursive case is going to be us using that number that I've given, and then it's going to be, I'm going to call the function again, and I'm going to say number minus 1. So what that will look like is, if we were to draw it out, yeah, well done, well done. If you can spell, that's okay. Spelling is not essential. As you can see, I make lots of spelling mistakes when I type, and I think my accuracy of typing has gotten worse as this term has continued. So what it looks like is if we call our factorial function on the first call, let's say we're going to give it, let's say I want to start with factorial of 5. Okay, that means my first call is going to give me the number 5 times factorial of 4, yeah, which is the number minus 1, okay? So then this function call is going to give me 4 times factorial of 3, okay? I've called the function again. So this time it's going to give me 3 times factorial of 2. Great. I'm going to call it again. This time it's going to give me 2 times factorial of 1. Okay, fantastic. Now I have a stopping case at 1. Okay, I know that I'm going to return 1 in this case. So now I'm going to build it back up. So this is going to return 1. So that means that this whole thing over here is equal to 2, which means that this is equal to 2, and this whole thing is equal to 6, which means that this is equal to 6. So now this is equal to 24, which means over here I have 24. And 5 times 24, what does that give me? 120? Yep. And that means that I can now return here 120. Okay, so you see how it went all the way down until it got to the stopping case, and then it built it back up with the numbers once it's got the numbers. So let's put it into code to see what is happening in our code. Okay, and I'm going to use this. So if n is less than or equal to 1, I'm going to stop. And what I will do is I will return 1 in this case. So I'm going to return 1. Otherwise, I'm going to have a recursive case where I'm going to return the number times calling that function again, and this time giving it number minus 1, so giving it the next thing. Okay, and then not forget the semicolon. All right, shall we see it in action? And then we can do some more crashing. Okay, so dcc factorial.c factorial. Let's run it. Just used a whole bunch of things that don't exist because this is called number. Where else have I stuffed it up? Oh, and here I only have one thing. Okay. Okay, here we go. Where did n come from? Theo, that is an excellent question. N came from my head, and it doesn't mean anything. It should not be n. It just appeared. There we go, much better. All right, let's run it. Okay, enter a number. So let's start easy. Okay, great. We know 5, 120. All right. Who wants to give me a higher number? Higher than 5. 5 is a great place to start because it just shows how quick and easy it was. And Lisa, I will come back to answer your question. Absolutely. Why it's less than and equal to and not just equal to. I will come back to it in a second. Okay, 456. Okay, you're not joking there. You went straight for the jugular. 456. Geez, that's not looking very nice, is it? Now, what do we think happened here? What do we think happened here? So look at this. It stopped at number 13. Okay, so what happens if I run it? Come on, down to the bottom. Let's see what happens when I run it. All of those numbers are great, and they're all going to crash me. So if I run it with 12, no problem. What happens if I run it with the number 13? Okay, it's going to crash. Now let's have a look why it's going to crash. What is it equal to when it's equal to factorial of 12? Okay, there is a reason why you're crashing, and that's because you're storing your number in an int. So there's only a certain number of bytes that you can store. So only a certain range of number that you can have. And you fast run out of this number when you have just an int, okay? Because an int is only 4 bytes and that impacts how much you can store. What if I change it to a double? Okay, let's see what happens then. Let's see what happens when I change it to a double. Is that everything? I think so. Okay, let's try it again. Let's compile it. Okay, I'm going to clear it out, and then I'm going to run it again. Okay, So this time, let's see it with 12, no problem. If we run it again, if I run it with 13, okay, do I still have an int somewhere? Because now it's telling me that it's still outside of the value of int. I must have an int somewhere. So, Richard, that is a great comment. GCC doesn't pick up a lot of the errors that DCC picks up. Okay, so DCC is made in-house to stop you from making these errors when you head out to the industry, so that you do not cause too many overflows when you get out there. Have I changed everything to double? My function is returning an int. Yep. Good pickup. That's right. Well done. Good pickup. So I'm going to give it an int and I'm going to return an int. Yeah. Very good. Okay. Is that everything? Did I pick everything up? Oh, I didn't mean to run it. Okay, let's compile it. Oh, now I have a %d in here. Okay, here we go. It's all happening. And compile, and oh God, now I've got too many LFs. I got overly excited because I've got it here as an int. Oh. See, this is what happens when I start changing things on the fly. Okay, here we go. Now we're running, and let's do it. Okay, let's do 13 now. No problem, we've got 13. How far do you think we can go now? What do we reckon we can do now? LF is a long float. What should I do? Should I try 25? Oh, 25 is still doing. Look at that beautiful number. Ooh. Okay, Lisa's pressuring for 456 again. I'm not sure how. Oh, what's it telling us for 456? It's had it. It's had it. It's not going to do 256. So 456. Okay, let's go a little bit. So 68. Let's try that one. Okay, still giving us 68. This number is bigger than Ben-Hur over here. And it might give you something more than that. I don't know, 75. But you see how it's allowing us to go a lot further. I'm not. Nope, 255 is too far. 100. No, 100 still letting me do 100, and so on and so forth, right? So you're going to get exactly. So that there are limits to what we're going to get to. And once we hit that limit, if I could calculate the factorials, yes, and someone's picked up, excellent. When you have your 25 factorial, the result is going to have some precision issues because you've been multiplying things out so many times now. So it's going to cause some serious precision issues. So it's going to be, it's all going to be a disaster. It's just, yeah. Feels like the egg puzzle from all those weeks ago. A little bit like that. That's true. The egg puzzle is actually a first taste of how you do a binary search. So once you do later years computing subjects, you can think of that egg search because it's an introduction to how you do a search through something. Maybe, or maybe you'll forget about the egg, but see, it's still there. Okay, so you're going to overflow at some point, in which case, it's going to obviously cause issues. This is not how it's not like a super fantastic way to write this piece of code, but it's super fun. It lends itself to recursion nicely. So how about we go crazy? Let's do the Fibonacci sequence now. Let me clear this and let's do a Fibonacci, because who doesn't love Fibonacci? Who knows what the Fibonacci sequence is? Who remembers the Fibonacci sequence from maths? I think it got used in maths quite a bit. Who remembers the Fibonacci sequence? Yeah. Yeah. Okay. People, excellent. Well done. Yeah. 1, 2. I feel like it's constantly used as an exercise in computing as well because it's such a fun sequence. You have to really think about it. So when you do recursion and when you learn recursive languages, so some computing languages are fully based on recursion, which is, mind blown. But this is usually one of the first examples you use to understand how that language works because the Fibonacci sequence is all about, picking up the one after it and then the one after it and then the one after it. So you are always adding up the previous ones to get to the next one and so on and so forth. So the sequence 0, 1, you add up these two numbers to get to the next one. Then you add the next two numbers to get to the next one. Then you add the next two numbers to get to the next one. So you always add the two previous numbers to get to the one after it. Okay, fantastic. Well done. I'm pleased that at least I'm not making you think, what's a Fibonacci? What is she talking about? She's mad. Although you might still think I'm mad, but at least the Fibonacci is okay. So what do we think would be the stopping case in this instance? What do we reckon would be our stopping case now? What do we reckon? And what do we reckon will be our recursive case? Yeah? Okay, equal to 0, definitely. What would I return if it's equal to 0? Okay, n is equal to n minus 1, not quite. So you want your stopping cases to be, so it's equal to 0, it's equal to 1. So the stopping case is always that it's equal to something, or it's, oh, I didn't go back to explain why in the factorial. I will go back to that, Lisa, sorry. I will go back to explain why it's less than or equals to, not just equals to. Okay, so where do I finish? I can't really, 0 and 1 is my last lot, okay? So I really can't go anywhere after that. So if it's equal to 0, I will return 0. And if it's equal to 1, because in a Fibonacci sequence, okay, you have to use the two previous terms to get the next term. So that means that the two starting terms are going to be your stopping cases because in this case, you need two previous things to make the one that you want, which means that your stopping case is going to have two items in it. So what happens is there's going to be two stopping cases, and that's going to be if the number is equal to 0, which is the first item of a Fibonacci sequence, and if it's equal to 0, then you will return 0 because that's what it's equal to. And then what's going to be the next one? If you're always using the two previous ones, then what's going to be the other one that I have for my case? Yep, excellent. So it's equal to 1 is going to be our other potential stopping case. So if number is equal to 1, then I'm going to return 1. Yeah, excellent. Well done. All right, fantastic. Okay, then what do I have then? What's going to be my recursive case, do we think? How do I build up my Fibonacci number? What do you reckon will be the recursive case? When Okay, what do you think? What will I increment I and n is from input? Not quite, but good thinking. That's a good thinking. So if this is my number that I say, if I want to have this term here, then I will add the one previous to it and the one previous to that. So what do you reckon could be my recursion? Where would I call my functions here? What would I call the functions on? So I'm doing something and I'm adding something and I'm doing something again. So if I were to draw it out, and this could be helpful if I draw it out for you. I've drawn it out before for the lecture. Hang on. I'm going to go past it. I'm going to go past it so that you don't see what I'm trying to say. Okay, so here we go. Let me draw it out. Okay, so if I have, can we see that, or is it too? Yeah, okay, so if this is my Fibonacci sequence, 2, 3, 5, okay. Let's see, I call a Fibonacci 3. Oh, someone's got it almost, Lisa, almost. Oh, yes, someone's got it. Fibonacci number -1, Fibonacci number -2. So if I'm sitting on this term here, I'm going to call it the one before it, number -1, and I'm going to call the one before that, number -2, because I want to add the two previous ones together to give me that one, okay? So if I have my number, then what I will have, Fibonacci number -1, which is the previous one, and Fibonacci number -2, which is the one prior to that one. So it will give me the two previous terms, and I'm going to add them up. So what does that look like if we were to draw it out? And I might use a 5, because then that will be, let me demonstrate it a little bit better. And let me put the board so that you can see what I'm doing. Okay. And this one is a little bit messy because for each recursive call, you're actually calling the Fibonacci twice. So you're calling function twice in each return. So Fibonacci 5 in that case is going to give me a Fibonacci 4 plus a Fibonacci 3. Yeah? Okay, great. So I've got that. So now I'll go to Fibonacci 4. That will give me a Fibonacci 3 plus a Fibonacci 2. But then over here on Fibonacci 3, that's another function call. So this one is going to go off and branch out as well. It'll give me Fibonacci 2 plus a Fibonacci 1. Okay, great. So now my 3 here is going to branch out again. I'm going to run out of space here. Okay, and this one is going to give me a Fibonacci 2 plus a Fibonacci 1. And this Fibonacci 2 here is going to give me a Fibonacci 1 plus a Fibonacci 0. Okay, and this 2 over here will be a Fibonacci 1 plus a Fibonacci 0. Now, okay, what do you notice about this diagram? So I've got a Fibonacci 5 here, Fibonacci 4, 3, 3, 2, 1, 0, 2, 1. What do you notice about this diagram? What is throwing itself at you, if anything? Thea, what's the second else if statement showing? So it's showing that there is 2 stopping cases. What is really kind of becoming apparent when you're using this function? Shall I do some highlighting? Haven't done highlighting. So look, I've got Fibonacci 3 here. I'll also have it over here. Then let's say I've got a Fibonacci 2 over here, but then I also have it over here, and I also have it over here. And then I've got a Fibonacci 1, which I have over here, over here, over here, and over here. So there is a lot of function calls that are repeated over and over again, because each time it branches, it's going to keep calling it, you know, over and over again. So this is going to be a really labor-intensive way to calculate something, because it's actually going to be doing double or triple the work, because each time it's going to keep calculating these out. So then what happens, okay, so then why does it return 1? Because the first two terms of my sequence are 0 and 1, okay? So if the first two terms are 0 and 1, what that means, because in a Fibonacci sequence I always add the two previous terms, that means that I'm going to have really two stopping cases, because it's going to stop when the two previous terms, you know, come together. So in my case, when I start building it up, so now I've got Fibonacci 1, that means I know what the answer is to this one. I know that that's equal to 1. I can return 1 in this case. I haven't even finished running because this one can go again over here. This can branch again to Fibonacci 1 plus Fibonacci 0. So you see, can you see from the diagram why we have the 0 and the 1 as well? Because when we break things up, we're going to get a 1 and a 0. So if you just have the 0, you're not really going to know what to do with the 1. So, okay, so we've got 1 here. This, I know, is going to give me 0. This one is going to give me 1. So that means that I now know that 1 plus 0 is 1. Is that right? Oh my gosh. So that's equal to 1. Now this is 1 plus 1 is equal to 2. So this one here is equal to 2. Okay, this is 1, this is 0. So you see how labor intensive it is to then build it back up and to calculate it out again, because you have a lot of repetition actually here. So this is 1, this is 0, 1 here. That means here we have a 1 also. So that's going to be a 2. So it's going to take me a lot longer to build it back up. And I hope I didn't make a mistake somewhere in my writing. But basically, it's going to, the Fibonacci one is an interesting one, because a lot of your function calls actually repeat themselves. So let's see it in action. Let's compile it and see what it does. Okay, DCC, Fibonacci.c, Fib. Okay, let's do 5. Okay, excellent. Should we try, let's throw me a bigger number than 5, because 5 obviously has a lot of repeated calls, but it still doesn't take that long. Yeah, because it's still a small number. So throw me a bigger number. Okay, so that's still fast if I do 10. Okay. Everyone is just very keen to break things today. 283,712. Okay, guess what? That was too much. I've overflowed the stack, okay? A common cause of this area is infinite recursion. What's happened is that there are way too many calls now happening, and it's overflowed the stack before it even reached the stopping cases, okay? So that was a very good example, but we kind of just jumped into it with no... Okay, so let me interrupt that. Let's go to a slightly smaller number to see what so let's try, how about 1,000? No, but it's fantastic, because you can see that actually that's really not going to work to do it this way, to use recursion in this function for such a huge number. Okay, notice I've now put in 1,000. Notice how long it's taking. Okay, notice how long it's taking, because it has to make so many calls out when it gets to 1,000. But it feels like it's still going to come back to me. It feels like it's still going to give me an answer. I've got high hopes. We could be here for a little bit. Maybe I went too hard, also too strong. Someone's suggesting a -1. That will definitely kill us as well. We can try that. That will That will kill us. Here we go. Ah, no, it was too much. It was all too much. It was all too much, but I was close-ish. No, I was way out. No, oh my gosh, it got to, where did it get to before it overflowed? 47 it got to before it decided that is just a little bit too much. And that is because what overflowed? My integer overflowed. So if I make it a double, I'll be able to go a little bit higher, but then I might overflow the stack, with the number of calls as opposed to the actual integer values. Yeah, so there we have it. So 1,000 was too much because it overflowed the integer value, and before it, 283,712 was too much because it basically overflowed everything under the sun. There was too many function calls, too much stuff happening, and it overflowed it solidly as well. So that's the Fibonacci sequence using recursion. How does everyone feel about that? Feeling good? Feeling confident? Recursing? Recursing? Should we try and do another linked list function? We've got 14 minutes. Should we do a linked list function with recursion as well? Should we try one more linked list function with recursion? Yeah, 283,000 was solid. It was really solid. Okay, let's do it. Let's do a linked list function. So I'm going to go back to here. I'm going to close the Fibonacci, the factorial, the infinite recursion, and let's go to our linked list. What should we do? Should we do ending a node at the end? I really do want to crash this computer. And I was just telling Tom right before this lecture that I really would like a new computer. And I feel like if I keep crashing it, then it really justifies in my mind why I need a new computer. Okay, let's do it. Oh my gosh, someone wants to do a linked list Fibonacci. Geez Louise, we could do it, but it will take me longer than 13 minutes, I think, to code that up. Let's do one where we add a node at the end. Let's do an add node at the end. Yeah, let's do an add node at the end. Okay, all right, so if we're going to have a function that adds node at the end of the list, what are going to be my inputs and outputs into this function? What is going to be my input and what's going to be my output? Is there a huge delay on me talking? And I didn't realize there was a huge delay. I've got such great internet right now. I'm just soaring high. The internet has been amazing. Okay. I'm excited. What's going to be input? What's going to be output into this function that adds a node at the end? So what will we give a function that adds inserts at the end? Okay, significant delay. I don't know why that happened. My stream is healthy. It's been healthy the whole time. It's been very exciting. It's just a joy to see that green dot that says excellent, because the first few weeks were not great. Yep, head is the input. Absolutely. We're going to give it the list so that we know where on earth we're going. Fantastic. And we are going to output the head as well. So we're going to output a struct node pointer. Okay, I've got this. Okay, so we're going to give it a struct node head. So we're going to give it the list into which we're inserting. And we're going to output the head of the list. Excellent. Well done. Okay, fantastic. All right, now we're going to need a stopping case. And we're going to need a recursive case. Now, if I can remind you, what happens is that in a linked list situation, when we insert at the end of the linked list, I'm having trouble pronouncing linked too. we want to traverse through this list until we get to the end, to the last node. We want to stop there, and then we want to insert. Okay, so what do we reckon we can do to make this happen? What do we reckon is going to be our stopping case? What do we reckon is going to be our recursive case? I'm probably picked a terrible function out on the fly, but I think actually it's a good one because the code is so much smaller for it. Do you want me to, I'll copy and paste the code from week 8 that has it in an iterative way so you can see what's going on. Hang on, so I'm going to go out of here and I'm going to go into week 8 and here it is. So I'm going to take out that linked list C. Okay, so you can see what it does iteratively as well because we've done it. We've done insert middle. We're not going to do that. Here we go. Insert end node. I'm going to copy it across so that you can see what it does normally, and then we can talk about what it can do recursively as well. Okay, so when we do it iteratively, we create a current node. Then we create the node that we want to insert by using the create node function that we have. Then we move through until we get to that second last node, until we get to the last node. We stop at the last node because then we want to insert after it. Okay, so that's the process for adding a node at the very end. So now let's have a look. So the stopping case we're thinking is head next is equal to null. Okay, I like that. So it's either head next is equal to null or it's head is equal to null. Where is it going to be? We can try it both ways and we can see what works, okay? So let's do head next, okay? If we stop at head next is equal to null, then we're going to stop over here, okay? Then we're going to insert it in. So we can try it and we can see what it does. Okay, so if head next is equal to null, then what do we want to do? Or actually, even the recursive case is easier. So what do you reckon could be the recursive case if we want to put it into the next one? So remember, if I've stopped here as my stopping case, how do I now, and I've stopped at this node, how do I now insert after it in terms of the recursive function? What do we reckon? So when I recurse, we're trying to add a node at the end of our list. So we're going to call our function again. Oops, I just started typing in the chat feed. So in the recursive case, we're going to call our function insert end, and we're going to give it something here to insert. So we want to think what is going to be, okay? So Lisa, almost, I mean, you would do a malloc, but that malloc can be done inside the function that you already have. So you're pretty good at this. What do you think you would be inserting with, okay? We're inserting into head next, aren't we? Because we're inserting after the last one. But remember that we're going to use this recursive function to move through our list. So if this is the head, okay, you're saying we're going to stop when head next is equal to null. So I want to get to the end of this list before I insert. So I'm going to go here. Is head next equal to null? No. Is head next is equal to null? No. Is head next is equal to null? Yes, it is. So what I want to do now is I want to create the node that I'm going to insert, okay? So what I will do now is I'm going to give it a node. So I'm going to call my function that will actually create this node for me. So, and I haven't even given it anything to insert. Oh, I have to give it a data here because it doesn't know what it's inserting. Okay, I'm going to create the node here and I'm going to give it the data, so the data that I wanted to have, and I'm going to give it a null because I'm creating a new node that will be inserted at the end. Okay, so that's me just creating a node. So when I get to the end, of this list, when I get to this one here, which is my stopping case, what I'm going to do is I'm going to create a new node and I'm going to return a new node. So it will then give me a little box here that's not connected to anything yet, but it is in there and it's ready to be connected. So then I want to do my recursive case that gets me to the end of the list, okay? So how will I do a recursive case? And this is not, so head next. Okay, someone's got it. Someone's got it. So here I really want to have a head next. And it's equal to. Then I'm going to use my insert and I'm going to call the head next after it. And I'm going to give it the value as well that I wanted to insert. So this will keep moving me through the list until I get to the end. We can see if it works. Now I need to draw it out again. I think I've gotten you a bit confused, I think, because this might not work either. Okay. Let's have a look. Let's have a look what it does. What am I DCCing? Oh, I haven't actually called it anywhere. Okay, so let's add insert at the end. And going to give it the head, and we're going to insert a 3 at the end. And then I'm going to print the list again. Okay, and then I really have to put it inside my other function as well. Here we go, and let me paste this one. Yep. Okay, and I actually have another function in here that I should probably, because I copied this one in, so I should put it in the .h so it doesn't complain. Although I'm not calling it anywhere, so it shouldn't complain. Okay, all right, here we go. Okay, let's try this now. So main.c, linked list.c, o. Right, something was always going to happen. What did I do? Return create node. I've called something different than what it wants, clearly. Okay, what does create node? What a terrible function that I chose to do, because it wants data first and then it wants. Okay, let's try this again. Okay, and now let's run it. Okay, and what has it done? Okay, we've got a bit of a situation here. Got a bit of a situation. Yes, well done. Someone's just picked it. Because what's happened is we've got 1, 2, 4 in the list. Okay, then we want to insert a 3. And where we are inserting, we're actually inserting it instead of this last node. And we're overwriting this last node because we're not going far enough for the stopping case. Our stopping case is if head is equal to null, then we stop, and that's when we create the node, okay? So because we're inserting it at head next. Okay, let's try it out. Let's try it out. Compile, run, and yes, now it is working because now we are in the right place to insert. I'm going to draw it out better next week because I've run out of time. This is the end of the recursion lecture. We will do more maybe not recursion, but we'll do, let's see, many more people have answered the poll. 83% want to do linked lists. So what I'll do next week is I'm going to, on the Wednesday, focus on linked lists properly. We have already done that, but even more. And I'm going to do similar questions to the types that you would see in the exam to give you a little bit of practice. If there is anything specific you want to do, feel free to reply to that lecture revision conversation forum post, and we can do that as well. Also, people are not loving strings, so we will do that on the Tuesday after we discuss the exam. I'll go over strings again and show you a few fun things that strings can do, and pointers as well. So I'll do pointers whilst we're doing all of those things in there. So thank you so much for tuning in to Recursion. I hope everyone is feeling confident and positive. Assignment 2, I hope, is going well. Remember that there are help sessions, forums, and also your lab time to ask any questions. I hope that you enjoy the rest of your week 9, and we are almost at the end of the whole situation that is called COMP1511, which is a little bit sad. I wish it went for longer. I'm not sure if you wish it went for longer, but all right, have a good one, and I'll see you all next week for some chat about the exam and some revision. Good luck. Bye.